if we talk about the parameters, we already saw that we have the position parameter, which is the center of the 3D Gaussian. So this is the position parameter mu xyz. It is the center of the 3D Gaussian. Now we have to optimize it. Now what is the meaning of optimization here? So see, the idea is that we will start with a random orientation, like random values for the parameters. So we will be having millions of 3D Gaussian with some random values for the parameters. It will generate an image which will be very different, which will be very different from the image which we are interested in. We call it the ground image, the ground truth and rendered image. So the ground truth and the rendered image will be very different. The goal of optimization is to tune the parameters, to set the parameters, to assign the parameters that value which will minimize the loss or which will bring the rendered image close to the reality. That is optimization. So when I will be optimizing, I have to optimize all the parameters. So if I talk about optimizing position parameters, the meaning is that I have to like get those values of mu for all the Gaussians. If I plug those values, the rendered image will be very close to the reality, the real image. So we will be seeing that position parameters, we will be directly optimizing it using gradient descent, wherein we will be updating the value of mu in order to minimize the loss. So what we will be doing, the interpretation, will be moving Gaussians to align with scene geometry. So optimizing position parameter is about optimizing the geometry. So the geometry, the scene geometry of the rendered image will be very similar to the real image. That's the goal. Now, if we talk about optimizing covariance, see, we cannot optimize the covariance matrix directly. See, optimizing covariance matrix, what is the meaning of optimizing the covariance parameter? First, let us understand that. Then we will try to understand why not optimize covariance directly. So optimizing covariance means we know that, okay, covariance, it is containing information about the shape, the size, and also the orientation of the 3D Gaussian. Now we have millions of 3D Gaussian and we have to like identify the information, like we have to tune the parameters for all the Gaussian, the covariance, so that the rendered image is very similar to the real image, because this covariance is affecting the image, because the shape, size, and the orientation of 3D Gaussian is affecting the image, and there will be one ideal value for all the Gaussians. It will be different for all the Gaussians, but we will be having one ideal solution. If we plug that, our rendered image will be very close to the real image, and that is what we are interested in, and that is what is optimization is about, to get that solution. Now we cannot optimize the covariance directly. Rather we have to decompose the covariance matrix. Now why we cannot what you call it, like optimize covariance directly? So the reason is that, see, covariance must be symmetric and positive semi-definite. So these are like two constraints. It has to be positive semi-definite and symmetric. And if we try to optimize it directly, if directly optimized, the matrix may not follow these two properties. It may become invalid, rendering will become unstable, and optimization will diverge. Because in order to optimize the covariance matrix directly, it has to be symmetric at all the points and positive semi-definite. And when we try to directly optimize the covariance matrix, because when we will be optimizing, we'll be updating the parameters, we will be updating the values in that matrix. So there might be updations which can make it unsymmetric. And if that happens, rendering will become unstable. We will diverge from the solution. And hence, because of these two constraints associated with the covariance matrix, that is that it has to be symmetric and positive semi-definite. And when we will be optimizing means updating the numbers in that covariance matrix. And when we will be updating numbers, we'll be updating it with a rule, like if we are using gradient descent or any optimization technique, it might happen that the symmetric property might get violated, and then it will fail. So the way for that is, in order to optimize the covariance, we have to decompose the covariance. We have to decompose the covariance matrix. And we decompose the covariance like this. So this is the way for decomposing the covariance matrix. So S is the scale matrix, R is the rotation matrix. So what we did is, rather it should be, I'll write it. So sigma is equals to R S S transpose R transpose. So this is the formula. Now in the covariance matrix, the diagonal is the S. We call it the scale. Here S is the scale matrix and R is the rotation matrix. So if we talk about the scale matrix, it is represented by a 3D vector, and this scale, what it like controls is the shape and the size of the 3D Gaussian blob. So it controls the Gaussian width and the size of the blob. Now this scale, here there is no constraint of it has to be symmetric or positive semi-definite. And because of that, because there is no constraint, it will always be valid. And positive values enforce valid covariance. And see, this scale cannot be negative. So scale will always be positive and it will always be valid. And one more matrix we are making use of is the rotation matrix. The R matrix is the rotation matrix, and as the name suggests, it will be containing the rotation information. So it will be a quaternion like this. So this rotation matrix, it will have like W, X, Y, Z. So see, angles, we can also have something called as Euler angles, which is like the information like how much angle it is making from the x-axis, y-axis, z-axis. So we are not using Euler angles, rather we are using quaternions. And why is it so? Let us understand. So see, with Euler angles, the problem is that gimbal lock discontinuous. This discontinuous is a very big problem, hard to optimize since it can be discontinuous. But this quaternions, no gimbal lock, it is smooth, and hence it is gradient friendly. Because we have to have it gradient friendly because we will be optimizing it. And if it is discontinuous, see what will be the problem, I'll tell you. See, when we will be optimizing it, what we will be doing is that at every iteration step of optimization, we will be assigning some values. What if the function is not defined in that value? So for that value, we call it discontinuous. So during optimization, it cannot be discontinuous. So Euler angle, the problem is that because while we are optimizing, we might get some angles which might not at all exist if we are going for Euler angles. But with for quaternions, since it is smooth, whatever value we are getting after optimization, that is valid. The 3D Gaussian is defined for that value. So now it's very clear that covariance matrix, we will not use it directly. Rather, we will decompose it into the scale matrix and rotation matrix. The formula will become R S S transpose R transpose. And this decomposed matrix, we can very easily optimize it. So when we will be optimizing the covariance, we will be optimizing the decomposed covariance matrix. So we'll be optimizing the scale and the rotation. And how we will be optimizing the covariance, let us look at that also. Now, what is the meaning of optimizing the covariance? It's very clear that, okay, we will start with some random values of covariance for the Gaussians, 3D Gaussians. It means all the millions of 3D Gaussians, it will be having different shape, different size and different orientation, and the rendered image will be very different from the real image. The goal of optimization is to find the suitable values of scale, shape, and orientation for all the millions of Gaussians, so that the rendered image is very similar to the real image. That's the goal, to find those values. So we have to learn. Optimization is about learning. Learning means getting those values of S, the scale, which will take the rendered image very close to the real image. So we will learn S, we will learn Q. So for optimizing the covariance, we have to learn the scale, we have to learn the quaternions, that's the angles. Then we have to convert the Q into R. R is the rotation matrix. Because once we get the quaternions, we have to convert it into the rotation matrix, and then we have to compute the covariance matrix using this formula, R S S transpose R transpose. And in this way, we are able to optimize the covariance. So idea is very clear. For every 3D Gaussian, we will be having a covariance matrix. We have to break it down into the scale. So we have to learn the scale for all the 3D Gaussian. We have to learn the quaternion for all the 3D Gaussian, millions of 3D Gaussian. And then whatever quaternions we learned, we have to convert it into rotation matrix. And for every 3D Gaussian, whatever the scale we learned for it and the rotation matrix we learned, we'll combine it and generate the covariance matrix. And that will represent the shape, size, and the orientation. And if we do it for all the 3D Gaussians, millions of 3D Gaussians, automatically the image we will be representing, it will be very, very similar to that of the real image. So it guarantees valid covariance. It guarantees stable gradients. And it guarantees physically meaningful shape. So this covariance we got after optimization, the procedure we are following, the decomposing it and then learning and then computing the optimized covariance, it will guarantee valid covariance, because now whatever covariance we will get after optimization, it will follow those two properties. That covariance will be symmetric and it will be positive semi-definite, stable gradients, and physically meaningful shape. So because these two properties of covariance are maintained, we will get physically meaningful shape. Okay, now we'll discuss optimizing the opacity. So first let us understand opacity more clearly. Then we will understand what is the meaning of optimizing for opacity or optimizing opacity. So see, each Gaussian, each 3D Gaussian, it has transparency, which is defined by this opacity. It will be a number between 0 and 1, including 0 and 1. So see, if this opacity, this alpha, if it is 0, it means invisible, full opaque. 0 means invisible, 1 means full solid, and 0.5 means semi-transparent. So see, the value of 1 means full opaque, value of 1 means fully solid, fully solid means fully opaque, and 0 means fully transparent, fully transparent means invisible. Because this alpha, as we go towards 1, we are making it more and more solid. The 3D Gaussian, it is becoming more and more solid, more and more opaque as it is approaching 1. 0 means full transparent. Full transparent means it is invisible. And if we are increasing its value, it is becoming semi-transparent. And then like opaque, then like full opaque for 1. So now it's very clear, the value of alpha. It is defining the transparency of a 3D Gaussian, and it's very important. Now in optimization, what we will be doing is that we'll be determining, determines contribution enables volumetric blending. Okay, so optimization we'll discuss uh, like after some time, but now first let us discuss why opacity is important. as a parameter. What role opacity plays? So see, we already know that there can be millions of 3D Gaussians which will represent a scene. These 3D Gaussians, they might overlap. So these 3D Gaussians, they will overlap with each other on top of, like there can be stack also, like depth will be there. And this opacity is very important. It will help in blending. We call it volumetric blending. By changing the opacity, we can change the blend. And that blend will basically this because of this blending, because of this, if we change this value of transparency of the 3D Gaussians, the blending will change, and because of that the reflection, the lightning, that will change, the texture, that will change. So the idea is very clear. Like let us suppose I optimize the position parameter. If I optimize the position parameter, so the rendered image made from millions of 3D Gaussians, its geometry will be very similar to that of the real image. Its geometry will be very similar to that of the real image. If I optimize the covariance matrix, then what will happen is that the 3D Gaussians, the shape, size, and orientation will be aligned in such a way that the rendered image is very similar to that of original image. Like now, I'm not just talking about the geometry, but also the shape, the objects in the rendered image, the edges, and all that. It will be very similar to that of the rendered image, original image. But still, lightning might be very different, because in original image there might be certain reflections, certain lightning conditions that will definitely be missing in the rendered image. So we have to optimize that. And how we can optimize that? By optimizing the alpha. So for we know that every 3D Gaussian will be having alpha associated with it. So we have to optimize, like we have to keep on changing the values of alpha for all the millions of 3D Gaussian until we find the solution. And that solution will be those values of alpha for 3D Gaussian. If we plug that, the rendered image will be having the lightning conditions, the blending, which will be very similar to that of the original image. So that is the optimizing opacity. Now let us look at the some one mathematical formula. It's very important. So rendering contribution. So see, if I talk about final pixel color, now what is final pixel color? Let us understand. See, the idea is that the final image we will get, it will be the collection of pixels. The final image we will get, it will be the collection of pixels. Now every pixel will have color value. Now how that color value will be obtained using this formula? So the final pixel color value will be the sum of alpha I into ci into wi. Now what it is, let us understand. Okay, so see, alpha ci is the color of a 3D Gaussian. Wi is the influence weight of a 3D Gaussian, and alpha is the opacity of the 3D Gaussian. So the idea is that we know that, like, for a pixel, for a single pixel, hundreds or thousands of Gaussians, they might compete, they might blend, because overlapping is happening. And in the final pixel color value of a single pixel might be determined by thousands of Gaussians. They might be overlapping, they might be competing, or not competing, rather contributing. So thousands of 3D Gaussians, they will contribute in determining the final pixel color. So what we do is that for every 3D Gaussian, we are finding the product of its color value and the influence weight and the opacity. See, opacity is the transparency. Now let us suppose we have a 3D Gaussian which should be on the top. So it cannot be very transparent, or it can be transparent also. It depends on the scenario. But now the idea is very clear that every 3D Gaussian, it will be having the opacity the color and the influence weight, and we will be considering this. Uh, so the idea is very clear. Final pixel color value, the value will be dependent on 3D Gaussians, thousands of 3D Gaussians they can contribute. So what we are doing is that for every 3D Gaussian, its color, opacity, influence weight, we are multiplying it and we are adding it with all other contributing 3D Gaussians. And this blend will give me the final color pixel. And hence, the value of alpha will be very important. And that is what we have to optimize. Because if we are using random values of alpha, so the color pixel will be very different. And if we optimize it, if we get the solution like the values of alpha, then the color pixel of rendered image can be very similar to that of the real image. And that is what is optimizing alpha is about.